Welcome and thank you everybody for joining us for today's C2 Smart webinar. I'm Lizzie, a research project manager at C2 Smart, which is a US DOT Tier 1 University Transportation Research Center. And we leverage recent advances in big data and technology to solve today's urban mobility challenges. Today's webinar is on the second phase of the project, Digital Twin Technologies towards understanding the interactions between transportation and other civil infrastructure systems. And we're joined by three presenters, all of whom are from the University of Texas at El Paso. The first is Dr. Calvin Chu, a professor of civil engineering at the university. And next we have Dr. Ruben Key, an assistant professor of civil engineering. And lastly, we have Talha Asfar, a PhD candidate and research assistant. And as always, we will be recording this presentation and uploading it to the C2 Smart YouTube channel. And we encourage everybody to ask questions. You can do so by pressing the Q&A button at the bottom of the Zoom window. And then we will read out your questions at the end of the presentation. And with that, I will hand things over to our presenters to get us started.
Good morning, can you hear me?
Yes.
Yes. Yeah. So my name is Calvin Chu. I'll be presenting the first part of the webinar. And this is actually the phase 2 of the project. There are 3 PI or co-PI plus many other students. So I'm Calvin Chu, or very long Chu, my name is here. We have Dr. Adiba Rahim, Dr. Jeff Weiner, and Dr. Reminka. Dr. K is the PI of this project. Next slide, please. Okay, so today's webinar will follow this outline. I'll do the introduction, and then we will talk about the goals we set for this project. And Taha will present the digital models, and we'll follow with the site selection and implementation and integration of the different components. And finally, we will show you the scenario analysis and the future directions. So what is digital twin? Digital twin is a visual copy of existing physical system combined with the bidirectional connection between the two systems, where they can exchange data in real time. And here, digital twin introduced the concept of electrical or digital representation of physical products, which in the past, the collection was manual, and now we are trying to automate the process. And in the past few years, there has been an exponential growth of digital infrastructure and sensor to do automated data collection of high resolution or fidelity. And digital twin has become a very popular research topic in civil engineering. Next, please. Okay. So in this project, we will first, these are the goals of the project. We will try to explore digital twin as a tool for management of civil infrastructure. In particular, in phase 2 of the project, our goal is to implement a smart living lab using the campus as an experimental site. And we are focusing on 3 infrastructure systems: transportation, construction, and planning. As for the scenarios, we use roundabout, one of the roundabouts on campus to do the data collection. We also selected the pedestrian bridge on the campus building, and we also extend the analysis to more fidelity or rarity. So these are the following tasks of our project. We start with digital review, and then we build a digital twin model and based off the campus, and followed by selection of the site, the roundabout, the bridge, and implement implement the smart living lab at the site by putting on sensors, establishing the communication, and develop the algorithm to process the data in the lab. As for digital model, the next step will be to develop the simulation model and perform some analysis and analytics of the data collected. And we augmented the data based on different configuration to display the results and connect with the digital twin with the real world based on some assumptions. And the last part of the project is to organize a workshop as part of our outreach activities to the local stakeholders. Taha, over to you.
Okay, thank you so much. Yeah, so when we started this project, we obviously started with a literature review to see what the state of the art was in this field. And of course, there was an extensive literature review, but let me just summarize the main points. We found that for infrastructure systems, like civil infrastructure systems, people were using sensors to get the real-time behavior from accelerometers, inclinometers, other transducers, pressure cells, temperature sensors to get building information. And this was incorporated into some BIM, like building information modeling systems, which are like data-driven approach and data-centric engineering approaches to plan how you can improve the efficiency of the building, for example, and make it operationally more convenient. And of course, like for future planning as well. If you scale out from like one building, you consider more buildings or a whole city. So that goes into the territory of smart cities. And those digital twins can be used for disaster management and for planning for future expansion and upgradation. And we noticed that when they were studying things like disaster management, there were also this huge potential for the future planning, like how they could like compare different scenarios and how the city can evolve in the future. We also saw LiDAR technology was being used a lot to create the 3D models, and specifically for, again, with the disaster management, it became very useful to have like a before and after LiDAR capture, which will tell you exactly how a hurricane, for example, has impacted a certain area of the city. Finally, we also noticed digital twin systems being used in intelligent transportation systems to manage and secure the traffic flow and predict it for the future and like cause changes based on the current conditions. And obviously, once you have the data, once you have the system set up, you can employ deep learning algorithms and detect vehicles automatically through the videos. So inspired by this, we decided to create some digital models. And before creating the digital model, we noticed there were some challenges that, for example, if you wanted to create just a road network simulation, it's very easy. You can go to OpenStreetMap and download the data from there. It's not going to be perfect, but it's good enough for a simple 2D simulation. If you want to add 3D, you can add like aerial LiDAR data. But if you're collecting it by yourself, you need a lot of equipment and computation, and it's a very slow and difficult process. Or you can use GIS mapping that has already been done, but that doesn't give you the exact visual fidelity. It might give you the good terrain, but not building models and specific locations. So we have also seen manual 3D modeling being used for autonomous driving research in softwares like Carla, and that's a good way to go. But of course, there's a limitation to how much manual 3D modeling you can do in one day. So you have to like if you're creating a large map, it's going to take a long time. And then on the functionality side of things, there are enterprise services like Microsoft Digital Twin, AWS, IoT Twin Maker, iTwin from Bentley that support digital twin applications. And if you have the building information modeling and sensors and everything, you can basically automate entire buildings using these platforms. But of course, these are paid platforms, and like you need a certain level of, shall we say, existing models and technology to build on top of this. So there seems to be no simple solution for a digital twin model that we can just start it with, and that motivated us to create our own that supports transportation simulations, for example. But even going down this road, there are, of course, further challenges that the road network information is incomplete or inaccurate, especially in university campuses, where I guess Google's Street View car does not drive that much. And then building information and 3D models cannot be directly used simply because they are not available. No single software solution exists to incorporate all of these models and data in a single place. So that framework also needs to be created from scratch. And if you want campus operation data to do like large scale, longer time scale studies, for example, that's also, in theory, it must be possible because that data exists somewhere, but that is not available. So adding to that, even once you have all of this, the scale of data, the scale of the digital infrastructure to get all of this high fidelity representation means that you have higher costs associated with obviously the hardware, but also the computation requirements. So there are bottlenecks in the system, and you have to efficiently manage the data. So this is what we did for this project. We created a campus digital model and road network based on OpenStreetMap and Google Maps. So it's basically a 3D model of the campus, the university campus, and can support road networks for traffic simulation and autonomous driving. This is the procedure. We took some open source data from OpenStreetMap, and you can convert the OSM to XODR, which is an open drive format. It just gives you the road network. Then if you want the 3D mesh, it can be gotten from services like Mapbox, which are free. But it has a small mesh size, but those are like small blocks. They're not very visually appealing. There is a way to download data from Google Maps, and this is the procedure that I followed in this method, using RenderTalk to get the 3D building information from Google Maps. And most of the software is open source or free software, except maybe Roadrunner, which is used to edit the road network and do lane markings and manual signal timing and things like that. It can be done in other ways, but I used Roadrunner for this. Yeah, as I said, RenderTalk is basically a graphics debugging tool that can extract 3D data from Google Maps. It's very useful to create these 3D meshes, which can then be imported into any 3D editing program, like Blender, for example, using the appropriate plugins. And here I have shown some of the map that is displayed in Blender right now. So of course, it contains the terrain, the buildings, the trees, and even parked cars. So you get everything that you see on Google Maps. Here are the software that I used. Carla is basically an open source driving simulator for autonomous driving research, and it is built as a game, basically in Unreal Engine, which is a game development platform. So once I got the map that you just saw, I was able to put it into Unreal Engine as a level in Carla. And I use Blender, which is open source 3D modeling. Roadrunner is a 3D scene editor for road networks. And finally, we also use Sumo, which can do co-simulation with Carla. So not only can you do the autonomous driving on the road, you can do microscopic traffic simulations to figure out where the congestion problems are, for example. And you can simulate vehicles, public transport, pedestrians. And here is how it eventually looked. The first picture is simply just the QGIS information of the OpenStreetMap that you download. It tells you the buildings and points of interest. The second is also intersections and waypoints on the road network. So basically, this is the road network in Roadrunner. The third picture is like I was talking about the Mapbox data. This is what it looks like. It's just blocks, so it's not very useful for any good 3D representation. In picture D, this is the top view in Unreal Engine, while you can edit this map so that it can run in Carla. And then E and F are these levels running in Carla itself. So they look very nice. Zoomed out, they look very nice. Of course, when you zoom in, the artifacts begin to show up, as you can see. So, sorry. So I was able to, sorry, something strange. Yeah, so I was able to use Google Maps data and create all of this, and the road network comes from OpenStreetMap with slight alterations to fix things that we know about the campus, but perhaps the Google Maps does not know how the roads go exactly everywhere. And it's composed of 1.59 million triangles, and it's running on an Intel Core i9 10900X CPU with 256 gigabytes of RAM and a GPU, which is very powerful and I guess overkill for this. But you do need, if you are going to create some, replicate this process and create a digital twin for yourself, you do need some serious computation power. Or you can use the Mapbox model, which has much lower fidelity, but also very fast to run. So there are the trade-offs. And once this model was deployed, you can see you can drive a car on the road, and there's different sensors you can attach to a car. You can attach LiDAR to it. You can have depth sensing. You can have optical flow, which is the relative velocities observed in the scene. And you can do finally co-simulation with softwares like vSim or Sumo. The other site that they created a digital model for was a pedestrian bridge, and this was a structural model of the bridge. Basically, the idea is to instrument the pedestrian bridge with strain gauges and tilt meters to see how it responds by the dynamic load of the pedestrians, and to track its aging through time, and maybe like some maintenance in the future. So Autodesk Robot structural analysis was used for the basically load analysis, and it can work with Autodesk Revit for BIM integrated workflows. So this was that is why this software was used. And this BIM integration enables the model to basically implement the sensors and analyze the bridge based on the physics simulation. And it is possible to create some real-time link with load and temperature deformations and use it with other software as well. So it's a very versatile environment with the Revit model that they're using. So like the structural model was created manually, but another model was created using LiDAR scans that collects the point cloud data. And because the bridge measurements were available, you were able to verify that all of the measurements are accurate, all the columns and pillars are of the right dimensions and materials, of course. And here you can see some screenshots of the bridge and according to the offsets in the model. Finally, the third direction of this digital twin endeavor was to explore extended reality, like virtual reality and augmented reality and mixed reality. To get started in this direction, they also used LiDAR to create 3D point clouds of different locations on campus, so we can see like different buildings in these VR headsets. And also it was able to create, more importantly than the exterior of the buildings, it was able to create the 3D models of the interior of certain locations like the laboratory, which I will show you later. And here are some specifications of this specific LiDAR, the Leica Geosystems. On the top right, this is basically the workflow of the LiDAR cloud capture. And on this bottom left picture, this is like one of the labs here. And you can see like how different things are labeled. These are obviously manually labeled, but there are deep learning solutions that exist that can get object recognition from LiDAR data, and this can be automated in the future. Now I'll talk about the site selection, how we decided to which places on campus we chose to create a digital twin of. And while the transportation network that I discussed earlier is of the whole UTEP campus, it's only the roads are not that busy. Only some roads outside the perimeter of the campus are busy, where people are trying to get in and find parking. So this was an ideal spot. It was right outside the Schuster parking garage, this roundabout, and it provides a good vantage point so you can observe the vehicles coming in and exiting the roundabout. It connects to the I-10 highway, the TX375 loop, the Can-Am highway, and we have often observed it to be congested at peak times in the morning and evening. So this was very interesting because one of the directions of the approach to this roundabout was undergoing construction. So this provided us a very, very good opportunity to figure out a comparative study of how would the traffic behave with construction and without construction. And we noticed there are much longer queues that extend all the way up the road. Here you can see this is where the roundabout is located. To the north is the university campus. The pedestrian bridge was chosen. It was located on the southeast side of the interdisciplinary research building, which is a new building, and it connects to the undergraduate learning center. This bridge was constructed recently, and therefore the construction drawings were available, which was an important factor because they needed to be able to verify all the measurements from them, and also to corroborate their LiDAR scans. This also left no ambiguity in what sorts of materials were used in what places, because they had all of those informations, so they could create a good physics simulation of the bridge itself. This bridge is used frequently by students in large groups. So when a lot of people are walking there, if you're standing on the bridge, you can feel those vibrations by yourself. So this provided an ideal place to install the sensors, just to demonstrate how pedestrian traffic and different weather conditions affect the bridge dynamic deformations. And here you can see right in the middle, this is where this bridge is located. We will see this in more detail later as well. It's a very tall bridge. It's like, I think the columns are something like 25 feet tall. And now let's talk about implementation. So now for the transportation part of the digital twin, we have a road network, we have the Carla simulation, but what about the data? Where will we get like real world data? So for this, we developed vehicle detection and tracking. And the core idea was this would be an edge computing paradigm. So the video would never be transmitted to the digital twin, only the pixel information, or the bounding box coordinates of the vehicles that are detected from the video. And this is based on NVIDIA DeepStream software development kit, which provides a complete pipeline for not just training your algorithms, but also deploying them specifically on edge devices. And the Justin Xavier NX edge device was used along with the camera on the 4th floor of the garage. The algorithms used specifically for this were YOLO V5 for the detection. It was fine-tuned for like specifically vehicle detection, and Deep Sort, which can track the vehicle and give us trajectories and maintain the same vehicle ID for a vehicle that it notices moving throughout the video. And this is so that we can get some real-time traffic flow information in all directions. And here you can see the architecture. Basically, there's a camera that looks at the roundabout. That video is processed by the NVIDIA Edge device. It creates detection results, which are simply plain text. And this plain text file is transmitted over the UTEP network to our lab computer, which is running the digital twin. And it was planned to be mounted in a NEMA-rated weatherproof box. So the elements don't get to it. The target detection and tracking algorithms also count the number of vehicles for every type, like how many trucks there are, how many cars there are, and so on. There are some errors when this video is processed. It basically comes from occlusion with other vehicles. If one car goes behind another car, then you lose track of it. And when it appears again, it is considered as a new car. So there were minor errors like this, which statistically they all even out over time, but in real time you can see them. Funnily enough, some of the biggest procedural hurdles from this came from the fact that we are installing a camera on a university campus, and it required approvals from the police department, planning and construction, facilities, legal affairs, the vice president of business affairs and IT. So it was like a long process, which is like in these projects, this is like the practical limitations are usually of that nature. So yeah, we obtained the real-time vehicle detection and timestamps for every past minute, what the flow rate was for each origin and destination of the roundabout. And on the edge device, the vehicle detection and tracking runs pretty fast, around 20 frames per second. The list of detections were refreshed every minute, hosted on a simple HTTP server running on the edge device, and it can be simply accessed by the IP over the Wi-Fi network. And on the client side, we had a Python script to convert those detections into counts and flow rates. So we can perform co-simulation with Sumo, which I will show later. For the bridge, these strain gauges were purchased, the Geocon model 4000, and it has a vibrating wire strain gauge. Basically, there is a wire inside and it is vibrating in different frequency modes. And if there is some strain or some deformation of the gauge itself, which is mounted mechanically to the columns or wherever, then the vibrating frequency will change, and that change will be picked up, and you can use this equation to measure the strain. And of course, like the software does that for you. And yeah, like I said, these strain gauges have to be placed using epoxy cement so that they move with the bridge. Here you can see all 8 of the sensors are shown here. They were not actually connected. This is not a field test. This is a bench test just to show that the sensors are working and they're working as expected. And the horizontal axis is, of course, time, and the vertical axis is like frequency. So if you see the yellow line, it should be just one frequency, but because it was given some deformation or like basically banging on the desk, you can see those perturbations. And this is like, in real time, this can be, of course, captured and incorporated into the digital twin. For the reality capture, they use the Leica BLK360 LiDAR, which captures point clouds at a rate of 1 million points per second and completes the whole scan in about 20 seconds. And the best thing about it, it maintains the positional information. So if you take one scan and then lift it up and move it to another location, and you do another scan, and if those scans overlap, it can automatically tell what the alignment is, and it can give you a pretty good starting point, and then you can go into the app, zoom in, and manually align the point cloud. So the picture you're seeing right here is the result of many scans. I think five or six scans all around the roundabout that we did, and this is all stitched together to make one single point cloud. Now, of course, these point clouds are very big, but that is like that is the nature of LiDAR point clouds. The idea was to get these models into the HoloLens, so you can have some augmented reality that you can see the model and manipulate it with your hands in this virtual reality environment. So the procedure is very simple. You export the file from the scanner as an E57 file in Cloud Compare, which is again an open source software, and you can adjust color, size, and alignments and export it as a PLY file. And then you need Unity, which is also a different game development engine. I talked about Unreal Engine earlier. Unity is another game development engine, and you can use that to develop the project file to be used in HoloLens through a Virtual Studio. And then once you have it in HoloLens, you can use your hand interactions and menus, and like in the air, you can manipulate this model and zoom in and do all those things. One use of this resulting model is to iterate the process for any like visual or functional improvements. Like, of course, the exterior of the building, like I said, is a very simple thing, but in the interior, this is very useful. Like if you have an empty building and you take a scan of the inside, and then you go back, and then you can look at it in virtual reality. You can place objects, you can do planning very easily. Like you don't need to be a dedicated engineer or architect to be like to be able to use this, because this is very accessible now that it's in this virtual reality environment. Oculus headset was also used, but that was only to display the Revit 3D models. Now let's talk about integration. We have all these different pieces. We have the model, we have some way to get the data. How can you integrate them? So the vehicles detected in the video are simply 2D projections of a 3D scene. They obviously don't correspond to the real location. So for every detection, we'll have the class, like is it a car, is it a truck, and so on, and the coordinates of the bounding box and the width and the vehicle ID. And if you follow these vehicles, you keep a record of where their coordinates are going, you can make these manual patches in the video frame to see where the vehicle is, has it crossed or not. And if you keep a count of this over time, you can figure out how many vehicles went from the west to the south, or from the north to the east, or so on. So you can create a whole OD, origin destination matrix. Finally, to correlate the points to the actual location on the digital twin, if you want to see a replication of those vehicles in the digital twin, it needs a simple linear transformation with the assumption that the ground is flat, which of course is not exactly true. The ground is not exactly flat, but that is, if you want to do a simple linear transformation, then this is like one of the easiest ways to do it. So the way to do this transformation is you just choose a few points. I chose 6 in this case. I think I chose more, but this is just 6, showing the 6 points here. And you just do a regression on these equations, because you have the image coordinates, you have the model coordinates, and you just do a simple regression to find A, B, and C. Once you do that, the vehicles show up on the digital twin in exactly the right place as you would expect them. But the detections from the video, because it is following the vehicle from one frame to the next, it is not exactly smooth. There are like jitters. There are significant jitters. So the easiest way to solve this, perhaps there are better ways, but the easiest way we took to solve this was simply to average the location from one frame to the next. So I have a running average to keep for every vehicle. And finally, because of the occlusion that I mentioned earlier, sometimes vehicles can disappear or reappear. So the list of vehicles becomes very muddled very fast. So every 30 seconds, this was refreshed. So we had fresh location information for every vehicle. And here you can see it in progress. The black area on the top is masked out because we don't care about the highway in the background. We're only looking at the roundabout. And this was like the result of, or the real-time, shall we say, mapping of the vehicles from the video to the 3D model. As you can see, it is still pretty jittery, but only in time. The location trajectories are actually very smooth. If you plot them out, they're very smooth, but temporally, because it works frame according to frames and not according to seconds, it looks like this. But of course, yes, this is there room for improvement here. For the pedestrian bridge, the specific sensors, of course, I talked about the vibrating wire gauge center and also a vibrating wire tilt meter to see the deviation from vertical. Those were also used. And then in order to utilize these sensors, components from Campbell Scientific, there was a CR6 automated monitoring platform, which is sort of like a microcontroller to log the data and to do some basic processing. And there was an 8-channel dynamic wire analyzer, which is like a data acquisition tool. So it all goes together. It works with a computer program from Campbell Scientific called LoggerNet. And then, of course, they have their configuration utilities and vibrating wire toolbox, and you can integrate it with something like, for example, like MATLAB to do some further analysis and processing. So yes, this was the VWire 300 was used to observe the sensor output in real time, and the CR6 can be used to log the results, which can be analyzed later, but it also has a provision for something like Ethernet, so it can be done in real time as well. Here's a LiDAR scan of the pedestrian bridge. And the placement of the gauges was basically placed away from the end of the struts so that local distortions don't affect the reading too much. The gauges measure along the y axis to capture the axial strain. There are 6 gauge locations I will show you. There's 2 gauges on every location to get a little bit of redundancy in the data. And because you don't need very fast update rates, and like you don't need a huge volume of data, the limit to record the limit to log the data was set at about every 20 minutes. And then, of course, because the way the sun hits the bridge, and like it can get hot, or half of it is hot, half of it is cold, and different time of day, there will be different expansion and contraction of the bridge. This sort of metadata of what time it is, what the weather is, this can be used for long-term behavioral analysis once you have, let's say, a few months of data. And here's just that sensor placement. All the red dots are basically the locations where these sensors were placed along the length of the bridge. For the extended reality, LiDAR scans were performed for multiple locations, outdoor locations as well as indoor locations. Here you can see another lab with specific items labeled. The thing about LiDAR is it's a very slow update rate. Like you can't just leave a LiDAR and keep it scanning forever. That would not be very useful, but it's very practical because structures do not change overnight. And basically, well, previously I discussed about the disaster management, and similarly, you would do a scan after something changes, like in indoor space. If there is a redesign, you go and scan it, and then you update your overall digital model. And the best part about this is that you can do modular scans of different parts of the campus, and you can maintain this catalog without like storing it all in one place. If you wanted to see one building, you would only be loading the model of that building, and you can explore it in your VR headset. Now, once this integration was done, it was time to do some analysis, and vehicles, we took a 15-minute video and we counted some vehicles, and we theorized about how the delay would be affected by closing one lane. Because as I mentioned before, there was construction going on the road. So we had the two scenarios, one with construction and one without construction. Yeah, so from the video, we manually counted where the vehicles were going, and also through the automatic counting from the vehicle detection. And we performed simulations. Of course, the automatic counting had some drawbacks, but because of occlusion and misdetections, but overall, it was surprisingly close to the real counts. And we found that without construction, based on the rates, flow rates that we observed, the average delay for a vehicle was 31 seconds, and with construction, it would be 34 seconds. So an increased delay of about 3 seconds. But these are very calm flow rates. So we did not observe it in heavy traffic. So if you double these demands in the four-lane normal scenario, this would now give you 32.89 seconds. But for 2 lanes, this now builds up the queue and you have congestion, and you notice an additional delay of like 16 to 17 seconds per vehicle. And this queue buildup was only observed in the 2-lane scenario. And practically speaking, these flow rates were not even that high. So it's like a significant difference when you remove that those 2 lanes. And from the video, here's a trace of all the vehicles detected over just 1 minute. So you can imagine the amount of data that is generated. Even though we're not saving the video, it's only text, but all of these points are logged for every vehicle through every frame of the video. And in 1 minute, we have a lot of points. So a lot of data smoothing and averaging was necessary to make sure that everything goes smoothly. And at the same time, we can do co-simulation visualization. So when the simulation is running on Sumo, you can also see those cars in Carla at the same time. For the pedestrian bridge, there was specific considerations for temperature and sun position, and different models were considered on how it would affect the materials of the bridge. The idea is basically that the different bridge materials will change differently, and at different times of day for the same kind of load, you would expect to see different waves on the sensor spectrum output. And what can be automated is that short-term monitoring can be done to establish a baseline of how this should behave during 1 day or like 1 month, and then compare it to the long-term behavior. Is there any deviation? And if you do notice any deviation, that will be cause for some predictive maintenance, for example. One of the things that this is useful for is to see if any nominal values are exceeded. But this is a very over-designed pedestrian bridge, and these values will not be exceeded. So in the simulation, like some values, some assumptions had to be made to see what kind of deformations there were. There are, of course, different scenarios for that. Like, let's say we assume there's a vehicle on it, or there's some sort of corrosion or scouring during rain, and that might cause some damage to the bridge. And so the idea was that this whole thing can serve as a platform, not just for predictive maintenance and real-time monitoring, but also for something like cost estimation and design iteration once you have that significant data collection. And of course, this was simply a showcase to the real thing, which would be that it should be scaled up to create monitoring systems for a larger bridge, another structure with complex dynamic loads, like, for example, wind loads. They did not consider wind loads in this scenario. But the idea is that something like this, with all the sensors and processing, can be incorporated into a larger digital twin. And finally, at the end of this project, we had a little workshop where we invited individuals, not just from the university itself, but also from local public transportation providers, Sun Metro, the city of El Paso, the Parking Streets Division, the Texas Innovation Alliance, which are a research group, and the El Paso Metropolitan Planning Organization. Just to discuss with them, not just this project, but also how the learnings from this project can be used in future endeavors. We set up 3 demo stations to show all our work to these individuals. The transportation network, digital twin of the roundabout, the structural digital twin of the bridge, and the VR and AR demonstrations for the digital twin. An invitational by the Texas Innovation Alliance was also introduced. This was also another research collaboration invitational meetup that they had. Yeah, so apart from just showcasing the project, the workshop discussed emerging technologies, grant readiness, and knowledge sharing between institutions. It was a very informative session. After the demonstration, there were breakout sessions for discussion of future collaborations. And here you can see on the top left, there's a demonstration of the bridge sensors. On the top right, there's the VR and AR. And on the bottom left, there's the road network simulation. And the bottom right is, I think, a breakout group discussion. Yeah, so the VR and mixed reality presented the structural model and the LiDAR scanned point clouds for the participants. The LiDAR scanner itself was also present to show exactly the process flow and how it works with an iPad app, and you can transmit it over the network. And then the breakout groups focused on ways to make the El Paso region more sustainable and desirable for private companies, for investments and development in the future. And we figured out some methods, discussed some methods to apply the digital twin technologies to make airport operations, for example, more efficient, to reduce the delays and costs. A lot of different ways of sensors and communications can be used for these problems. We also discussed feasibility of a public transport route from Fort Bliss to the downtown area, because that is a high demand route, but public transport does not exist on that. And then there were further discussion of vulnerability of road users, transit efficiency, and transit oriented development on Alameda Avenue, which is a road that connects the 2 US Mexico border crossings. And as this is a border town, this is a very specific concern for individuals here. And we also studied safety in the context of road usage, how cameras or sensors can be used to detect not just traffic parameters, but also pedestrian presence, especially in these areas near the border where there are actual safety issues. And the final breakout group focused on the use of connected vehicles as an application for the innovation zone. So like at these ports of entry on the border, they're notorious that for their, not just for the amount of traffic and time you have to wait, but that you don't know in advance. When you get there, you're suddenly stuck for a long time. So this can cause crashes, backup, traffic jams, and a lot of idling emissions, actually, which reduce the air quality. So one thing that can be done is queue length sensing and parking reservation systems, and maybe a smartphone app that can inform users before they get there that, no, oh, this port of entry is very busy, maybe you can try a different one, or you can park your car, and so on. Like the many quality of life improvements can be had using these systems. So to conclude, our project team achieved the following goals in this project. We were able to demonstrate what a digital twin for civil infrastructure can look like. Basically, there are many different things you can do with it, and there are many different problems you can solve with it. And we only touched on a few of them related to transportation or structures, or just the visualization in this augmented reality or virtual reality space. And we discovered that if you wanted to just get started on a transportation digital twin at the very least, there is a method to do so, and we created this whole pipeline of how to just get started on it without being very specific for the on the details, getting caught up in the details. And we were able to select specific sites to showcase the different aspects of infrastructure analysis, the roundabout for the transportation aspect, congestion and queue lengths and all of that, but the pedestrian bridge for the structural analysis, and the IDRB building was used as the location for indoor LiDAR scans, just to see how the data collection worked. Finally, we identified the data and data collection practices for reality capture to create these LiDAR scans and these 3D scans of big buildings and multiple locations on campus. You can't just literally keep doing that and adding to a single project. It has to be managed in specific ways. And we tested the digital twin pipeline with real-time visualization and real-world data-driven analytics in the co-simulation that I showed earlier. Finally, we explored different scenarios with real and synthetic data. Once we had that data, once we had the models, only then you can do that scenario analysis, and you can just create whatever scenario you want. But of course, we based it on real-world assumptions and augmenting the data that we collected with some real-world practical assumptions on how much, let's say, the demand would increase. The key idea, philosophically speaking, is that these designs have to be scalable to create modular, task-specific, and interconnected campus digital twins. If you incorporate these practices from the design stage initially, and you employ these extended reality and digital twin technologies, it can be a very useful aid in visualization and life cycle planning of the whole project. We were also, through our endeavors, identify gaps in the university operating procedures so that we can, maybe in the future, it will be easier to conduct such studies and like streamline these processes and create like a standard operating procedure for creating these models. Finally, we were able to disseminate the results and educate the local public stakeholders about digital twin technologies while brainstorming ideas and making plans for future collaborations. One future direction can be an interoperable software platform that can consolidate all of the different kinds of data and different approaches into a single platform where you can click on, let's say, one building and then go to the model of that building, or you can click on a roundabout and go to the model of that roundabout. That can be a future direction of continuing this research. Basically, all of these different things can be incorporated into VR and AR as well. And then finally, manual decisions that were being made for all these years, now can be considered domain knowledge and be added into automated systems to close the loop on digital twins to help make those decisions for you automatically. And that's it. We have 2 papers that were published in the course of this project. Thank you. And some references.
Great, thank you so much.
Thank you.
And as a reminder, we invite all questions. So please enter yours by pressing the Q&A button. So we have one that's already answered, and then we have another open one, which is, how did you merge or stitch scans from LiDAR? I might have missed this since I joined late.
Yes, so well, it was done in 2 stages. The first is that the Leica Geosystems LiDAR that we used, it comes with an app. And in that app, as long as there is like some minimum percentage of overlap between 2 point clouds, it does a very good job of fitting it by itself automatically in the app. There is a need to go and do some manual adjustment later, and that can be done in software like Cloud Compare. And that was also done for the larger scan that you see here. because this was like multiple scans or joined together.
Great. And we can give it another second, but I think that might be our last one. And if so,
sorry.
sorry, continue. Go ahead.
Sorry, in addition to what Taha just said, I think the LiDAR scan, how to stitch it, that's part of, I think, the phase 1 project, which was done last year. I remember there's some algorithms developed by Dr. Jeff Weiner's master or PhD student. So I remember one algorithm used was the ransack algorithm. You may have heard about it if you did like some image stitch as a similar algorithm.
Great. Well, thank you everybody for joining, and to our presenters for today's webinar. A recording will be made available on the center's YouTube channel and our website, where you can also find information about both phases of this project. And this webinar was brought to you by C2 Smart and the USDOT's University Transportation Center program. So thanks again, everybody, and have a great rest of your day.
Thank you so much. Thank you.
Thanks.
Thank you. Bye-bye.